Welcome everyone to Unit 2. Myself Shamli, Assistant Professor SVC. So we will explore the fundamental building block of how computer sees. The unit moves beyond simply processing pixel to extracting the meaningful information from images. We will learn to give a computer language to describe the visual world, which is the crucial steps towards true machine perception. The core idea from the pixel to perception. Here, the human brain does not see a grid of colors. It sees the object, shapes, and texture. Our goal is this unit is to enable computer to do the same. This is achieved through a set of powerful techniques that can be grouped into two main categories. The first one is the feature detection and matching. And the second one is the segmentation. So in the feature detection matching, this is about finding and describing the most important landmark in an image. We'll start with the point and patches and so on in this area. And the segmentation is the next level of visual understanding. Instead of just finding a few features, segmentations is aimed to partitioning the entire images. So these are some of the interaction for these topics. Let's go into that. So let's start with how computer sees. So in this first session, I described it into three types: part 1, part 2 and part 3. The first part is that why of the features. So when you look at your friend's face, you don't process every single skin cells, right? You look for a key features, a unique mole, the corner of the eye, the shape of the mouth. These are the landmarks you see or you use to identify them. In computer vision, we give computers the same capability by teaching them to find and remember points and patches. A point is just a technique, descriptively pixels locations like a sharp corner. A patch is a small area of pixels around it. The goal is to find points that are stable, meaning they look the same even if the images is rotated, scaled or as different lightning. A classic way to find these points is by looking the corners. Why corners? Because they are stable landmarks. A corner is a point where the image brightness changes a lot in a multiple directions. I'll show you how a Harris corner detector finds these points by sliding a small windows over the image and measuring how much the brightness changes, as we've seen in today's meme template also. The second part is that how of the descriptors. So just finding a point is not enough. How do we remember it? We create descriptors, a unique fingerprint for each patches that are used in CIDs to find the thief. So this is where the things get really interesting. Imagine you have two pictures of the same buildings, but one is taken from a different angle and it is a bit blurry. The computer need to find the same point in the both photos. This is a tough job, right? So that's why we use a powerful algorithm like SIFT and SIRF. The SIFT stands for Scale Invariant Feature Transform. It is a bit of a mouthful, but the concept is brilliant. It is find points and create descriptors that are robust to change in scales and rotations. It's like a superhero for features. We use here for a fingerprint matching. And the SIRF is a faster version of SIFT, often used when speed is priority. The another fast and a simple algorithm is the name itself is FAST, F-A-S-T, which stand for features from the accelerator segment test. It is a high-speed corner detector, perfect for real-time applications like on a mobile phones or a robot. And what about the blobs? The blob detector is another types of features detections that look for bright or dark circular region in an image. I'll show you a quick diagram or an explanation of how these descriptors works and how they are enable the feature matching, which is a process of comparing the descriptor to find the same point between two images. So the part 3 is the last thing for the width and matches, pointer match. So why it's all this important? What can we do with it? The answer is a lot. The ability to find and match the point in the foundation for some incredible application. That is what about your phone's camera. When you create a photomatic or the panoramic photos, it's taking the multiple pictures and using the SIFT as we discussed earlier to find the matching point between them. It then uses these points to align an image and stitch them together seamlessly. That is a perfect real-time examples. This same technology is used in augmented reality AR/VR, where the virtual object is anchored to a real-world object. It is also used in robotics for navigations and in object recognitions. It is a core of a computer's ability to recognize, track, and interact with the world. Next, we are going to see about the edges and line. So we are continuing our journey into how computers sees, right? So we are talk about the points and the landmarks in an image. Now let's talk about the outlines. What gives a picture its structures, right? The edges and line. So what is an edge? An edge is a boundary where the brightness or the color of the pixel changes dramatically. Where we have seen in memes or any social media platforms, there will be one stone is given. The upper part is more lighter and the darker in the lower part. The middle slide is a merge of those to find the color changes over that. So think of a black book or a white table. The line where they meet is a clear edge. To a computer, this change is a gradient, a measurement of how much the pixels values are changing and in what directions. The whole point of edge reduction is to find these gradients and turn them into a clear or clean line. A simple way to do with this is a Sobel operators. It's quick and easy filters that highlights all the sharp changes, but the result can be a bit messy as well as thick. So for a much better result, we use the canny edge detectors. It is a gold standard and it's a multi-step process that are very smart. It first blurs the image to reduce the noise, then find the gradient thins the edge down to 1 pixel wide, and finally connects the broken edge segments. This gives us a clean, continuous outline of the object. So this is the first part of this topic, the edges and line. So the second part is that finding the line. Once we have our edges, we often want to find the specific shapes like straight lines. But how do you find a line in a messy image? There is where there comes the Hog transform. It's a brilliant trick. Instead of searching for lines directly, it makes every pixel vote for all the possible lines it could be on. The line that gets the most votes, it's the one that actually did. So for instance, all the pixels on the single road line would all vote for the same line, and it would get a very high score. The probabilistic Hog transform is a faster version of this, which helps with the real-time applications by randomly sampling pixel instead of checking every single one. So we are coming to the end of this topic, that is so what. So why this is so important again? So the ability is to find the edges and line in the foundational skill for the computer is to understand a scene. In a self-driving car, for instance, the computer does not need to know what a road is in a human sense. It just needs to know where the lines are. It uses Hog transform to instantly find the white or yellow lines on the road and uses the information to stay in the lane. This is a perfect real-time example for single algorithms, or the simple algorithms enable a complex task. The properties of these edges and lines, like their length and orientations, can also be stored as descriptors for more advanced tasks like object recognitions and robotics. The next things we are going to see about the image segmentations part by part. So the first part is the concept of the segmentations. Today we are moving from finding individual features and the line to a bigger concept. That's what we call as the image segmentations. So in an image as a gradient or the giant grid of the pixels. Segmentation is a process of partitioning that grid into a multiple segments or the pixel sets. It's like a computer's vision of a color by numbers book, where every single pixel is assigned a label This transforms a sea of numbers into something meaningful like sky, road, or car, for example. So, thresholding, as we have seen in Unit 1 itself, is the simplest method. It's like a basic filters. You choose a value, and every pixel above the value gets one label, example object, and every pixels below gets another label, example background. It's quick but not very precise. So the region based segmentation is a bit smaller. It groups pixel based on the similarity criterions such as color or a texture. For example, a region groaning algorithm starts with a single seed pixel and expand outwards, adding all neighboring pixels that are similar to it. So what will be the second part for the image segmentation is that advanced segmentations method. So let's start with the watershed segmentations. It is a powerful and intuitive method. It treats the image like a topographic map with the pixel intensities values as elevation. So lighter pixels are high points and darker pixels are low points. If you flood this landscape, the water will fill the valley and the ridges will come or become dams, which are the boundaries of our segments. It's effective but can be sensitive to noise. So clustering based segmentations use algorithms like k-mean clustering to group pixels into clusters based on the color and position. It's like sorting a pile of marbles by color without knowing how many colors there are be front end. So the algorithms finds the most common color groups and assign a pixel to them. There are two main goals for modern segmentation. The first one is the semantic segmentations. The task is to clarify or classify every pixel in an image to a corresponding class label, such as road, tree, or a person, for example. It does not differentiate between the individual object of the same class. The next is the intersegmentations, where this goes a steps further by identifying and labeling each individual object. For example, it would recognize two different cars in an image and label them as a car 1 and car 2. And we are coming to the last part of this topic is that applications and evaluations. So why is segmentation so important? It is a core component in many fields. For instance, in autonomous driving or automatic driving vehicles, the car system must perform real-time semantic segmentations to understand its surroundings. It needs to know which pixels are the road, which are pedestrians, and which are other vehicles. In medical imaging, it is used to isolate specific automobile structures or diseases. A doctor can use it to precisely outline a tumor on an MRI scan or CT scans, so allowing for accurate measurements and treatment planning. This is a crucial real-time applications. Finally, how do we know if our segmentation is any good? We use the evaluation matrices. A common one in the IOU, intersection over union. We are studying in mathematics, which measure the overlaps between our predicted segments and the ground truth segment. The higher the IOU, the more accurate our segmentation is. The next we are going to see about the split and merge. So again I am going to distribute it into three types or the three parts. The first part is the core idea of this. Let's discuss on that. So we are talking about the segmentation techniques like split and merge. It's a method that both a top-down and a bottom-up approaches, which makes it quite unique. The core idea is simple. You first divide an image into smaller parts and then you put the similar parts back together. It is a recursive process that perfect for finding regions that are not fixed shapes like square or circles. So interactions. A simple and split and merge algorithm is a segmentation method, firstly, that first break an image down and then reassemble it based on the similarities. The split stage is that the first step is the split stage. We start with the entire image and check if it is uniform. This is based on homogeneity criteria. For example, we might check if all the pixels in a region have similar color or texture. If the region is not uniform, we recursively divide it into 4 equal subregions, creating a structure that can be represented by the quartet. So this process continues until all regions are homogeneous. Next one is the merge stage. Once image is split or after the split stage into a bunch of uniform, the smaller regions we begin with the merge cells or the merge stage. We look at all the adjacent region and combine them if they meet the same similarity criteria. This process continues until no more regions can be merged. The second part here is a practically and limitations. So the power of this method lies in its flexibility because it splits the image based on the content. It can produce segments with arbitrary shapes, unlike methods that use fixed size grids. This makes it a great choice for segmenting objects with complex organic outlines. However, like any algorithms, it has some limitations. The computational intensive. The recursive splitting process can be very demanding on a computer resource, especially for a large complex images. Second one is sensitive to homogeneity criteria. The final segmentation result is highly dependent on how you define. That's what we call as a uniformity. A bad choice can lead to over segmentations. that is too many small regions, or under segmentation, too fewer larger regions. The third part of this is that real world applications. So where this method is actually used, why we are going to study about this. It is particularly useful in applications where the shapes of the segments are irregular and unpredictable. So a real-time example, I will say a great example is the quality control on the manufacturing line. And automated systems can inspect a product surface for defects. If a defect is a different color or a texture from the rest of the product, the split an image algorithm. On other applications, I can say it is also widely used in remote sensing to classify the land covers types from satellite images. So, for example, it can segment forests, water bodies, and urban areas based on their spectral characteristics. So, compared to other methods, that is, other real-time examples or the computational intensities, there are some limitations. But while comparing with other methods, it's more flexible than a simple thresholding, as we have seen in the unit 1, but can be less precise than advanced segments like graph-based methods. It is a classic example of a powerful logical segmentation approaches. So that's what we have seen in this entire unit for the topic of that. So the next topic or the unit 2 is that edges and line. So again, I'm going to divide this slide into 3 parts: part 1, part 2 and part 3. So in the part 1 we are going to discuss about why these edges. So let's move into mean shift and mode finding. The first one is the intuition of mean shift. So we are going to talk about the segmentations method again. That is a bit different. The mean shift is that, unlike other methods that look for edges or specific shapes, mean shift is a non-parametric clustering algorithm. This means it does not assume anything about the data structure. Its goal is to find the modes or the peaks of a data distributions. The core idea of this is that imagine you have a bunch of dots scattered on a graph. The core idea of a mean shift is to repeatedly move each dot towards the center to the nearest cluster of the dots. If it is an iterative process, you pick a dot, find the average, that is what is called the mean, and the position of all its neighbors, and then shift the dot to that average position. You repeat this or repeat the process for every dot until none of them are moving anymore. It's a final stage. At the end, all the dots will have the converge on the peak of the data distribution. So what is the segmentation process in the mean shift? To use this for segmentations, we think of each pixel as a data point in a feature space. This space can be just the pixel's color or the combination of the color and its position, x or y coordinates. The mean shift algorithms then clusters these pixels. All the pixels that converge or the same peak are considered, but the same segments. This is especially good at creating smooth, continuous region. The next part we can say about the mechanism and the parameters in this. So how does this works under the hood? Mean shift is closely related to kernel density estimation. We call this as a KDE. So KDE is a way to estimate the probability density functions of your data. The modes or the peaks of this estimated function are what the mean shift algorithm converges on. The bandwidth parameters here is the most crucial element in a mean shift. It's the bandwidth parameters. So, this parameters controls the size of search windows that the algorithm uses to find a pixel's neighbors. A small bandwidth means a small window, which can lead to over-segmentations that I call as too many small segmentations. A large bandwidth means a large window or a big window, which can lead to 100 segmentations that we call as too few overlay large segmentations. So choosing the right bandwidth is a key challenge, but it's essential for getting the good results. But what are the benefits? A huge advantage of mean shift is that it does not require prior knowledge of the number of segments you want. Unlike algorithms like k-mean clustering, where you have to tell it to find a 3 or 5 cluster in that each set. So mean shift discovers a natural number of clusters in your data on its own. But what are some limitations for that? The main limitation it is high computational cost, especially for high resolution images. The iterative nature of the algorithms can make it quite slow. So these are some of the limitations of the mean shift, as well as some of the advantage of that. So now let's discuss about the real world applications. So mean shift is more than just a segmentations tools, right? So it is versatile algorithms used in several areas of computer visions. So there are some of the real-time applications, starting with the video tracking. So it's very famously used for the object tracking in the videos. So the algorithms tracks an object by finding the mode of its color distributed in each new frames. Just imagine how it works. For example, if you want to track a red car, you find the center of the red cluster in the first frame itself. And then the next frame, you just look for new location of that same cluster. So the process will be repeated until it really find out. The other application is that it is also used for discontinuity preserving smoothing, where it can smooth out an image while keeping important edges intact, because it is a clustering algorithm, right? So it is also useful for general data analysis and pattern recognitions. So these are some of the real-time applications. Let's talk about the relationship to clustering. While it is a clustering algorithm, it's a key difference from k-mean clustering. It is the ability to automatically determine the number of clusters. So this makes it a great exploratory tool when you don't have a clear idea of how many segments or groups are in your data. So there are a lot more about this mean shift. So next we are going to see about the normalized cut. Again, I've distributed into part 1, 2 and 3. So in part 1, the intuitions of graph cut. So we are exploring on the normalized cut, which means a powerful and elegant method for image segmentations. It is a graph-based approach, of course. So which means we first need to rethink our images. So first one is about the image as a graph. So imagine your image as a vast networks or a graph connectivity. Each pixel is a tiny dot or a node in that network. The dots are connected by lines, or we call as edges, to their neighboring pixels. The key idea here is that the strength or the weight of these connections or the nodes connections reflected how similar the pixels are. For example, two pixels that are same color would have a very strong connections, while two pixels of different color would have a weak connections, right? So the cut gradations here. Our goal is to segment the image by cutting this graph into a different pieces. A good segmentation is one that separates the dissimilar regions. So a good cut is one that serves only the weak connections. We call it as a low cost, while leaving the strong connections intact. The problem with the simple cut is that the most straightforward way to do this is to find the minimum cut, the one that has the lowest total cost. However, a simple min cut can be problematic. It might just cut off a single or isolate the pixels because it is so easy to do so. So the result in a very unbalanced way and unhelpful for segmentations. The part 2 of this slide is that the normalization cut solution. So here, this is where the genuine of the normalization cut comes in. It solves the unbalanced cut problem by changing the objectives, right? Instead of just minimizing the cut cost, it normalizes that cost by how connected each resulting segment is. The forces the algorithm to find the cuts and create the balanced partitions. Imagine the cuts. So now the normalized cut objective is to, the algorithm's objective is to find or defined by a simple yet powerful formula. It looked for a cut done as a low-cost relief or relatives to the total connections within each segment. This encourages segments that are well connected internally while being weakly connected to each other. So next we say about the mathematical solution. The solution is to this problem is to found through a simple algorithm instead of it's found by solving a generalized value problem. This mathematical approach might sound complex, but the important takeaway in this that the algorithms find the optimal cut by analyzing the eigenvalue or the eigenvectors of a special matrix derived from the graph, or we studied in a mathematical problem itself. The second smallest eigenvectors gives us the best way to split the graph into two segments. So let me explain about the steps. The process is follows. First one is to construct the graph from the image, where pixel similarity determines edge weight. The second one is to set up the mathematical problems using the graph properties. And the third is to solve the eigenvalue problems to find the optimal eigenvectors. The partitioning the graphs based on the signs of the eigenvalues, basically. So these are the some of the process or the steps involved in this. And the third part of the slide is that practically and applications oriented. So we have seen about many things, but what are the benefits of the normalized cuts are significant. It produces a good globally optimal partitions as we discussed before. So meaning it finds the best possible segmentations, gives the graph structures. The resulting segments are coherent and visually pleasing. But there are still some limitations over that. However, they are trade-off. The process of solving the generalized eigenvalues problems is very computational expensive, especially for large images. This makes normalized cut unsuitable for real-time applications where speed is critical. Because of this, it is really unsuitable for the real-time applications. But there are still some real-time examples. Despite its limitations, It is a highly effective for non-real-time tasks. It excels at segmentations of the complex natural scenes with varied textures and colors, where others' methods might fail. For example, it can beautifully segment a landscape photo with distinct regions of grass, trees, and skies. So, this is the best way of the normalized cut so far. So, what are the applications? The normalized cuts remains a seminal paper in a computer visions and is widely used for image and video segmentations, particularly in academic research and applications where high accuracy is more important than speed. It laid the groundwork for many subsequent graphs and spectral clustering methods. So the next topic is graph cuts and energy based methods. So what is a core principle in this? So one of the most powerful framework in computer vision is graph cuts and energy based methods. The core idea is simple. We redefine a complex problem like image segmentation as a problem of energy minimization. Think of it like this: the computer's job is to find the solution that has the lowest cost or energy with a minimum effect, right? So, the energy minimization framework is that cost is defined by the energy functions. That are the two main components. So, energy is vice versa equal to the cost over that. So, the data terms here is that this part of the energy measures how well the segmentations fits a raw image data. For example, if you are trying to segment a car, this term penalizes us for the labeling a bright car colored pixels as background. It ensures the solution in true to the image. The next is the smoothness term, right? This part of the energy penalizes the solution that have jagged or non-smooth the boundaries. It encourages the pixels that are to each next to have the same label. Example, a car or a background. Unless there are good reason for them to be different. This makes the segmentations look natural and coherent. The final segmentation is the one that minimizes the sum of these two terms. So let's talk about the graph presentations here. So this is where the magic happens, right? We can model this energy minimization problem using a graph. So what are the components in graph? Nodes, special nodes, edges. So nodes is nothing but every pixel in image becomes a node in our graph. So what is a special node? We have two special nodes, a source. We represent it with the S and represent the foreground, the object we want to segment. and the sync T represent the background. So these are the two things we called or mention it as a special note. Then what about edges? We create again two types of edges. One is T-link and N-link. So T-link is nothing but the edges from the source, yes, to the each pixel node, and from each pixel node to the sync T. The weight on these edges are determined by the data term. A strong edge from S to the pixel mean. It's very likely to do the foreground pixels. Then what about the end links? The edges that are connected to the neighboring pixels nodes, the weights on these edges are determined by the smoothness term. A strong edge between two pixels means they are very similar and we will pay a high penalty if we cut that connections. That is what we call as assign them in different labels. So what is the solution for this? Now that we have our graph, right? So the problem of finding the minimum energy is to transform into a problem of finding a min cut. So what is this min cut or max flow theorem is? So the fundamental principle that makes this all works in a min cut or the max flow theorem is that it states that the value of the maximum flow from the source, yes, to the sink, T, is equal to the capacity of the minimum cut. A cut is a way of partitioning the graph node into two sets, one containing the S and other containing the T, as well as we discuss source and sink. The capacity of the cut is a sum of the weight of all edges that are cut. So by finding the minimum cut, we are effectively finding the lowest cost way to separate the graph into a foreground and the background, the separation sets. So the cut itself gives us our segmentation boundary. Efficiently, algorithms exist to solve the max flow problem or the min cut problem, which in turn gives us the min cut basically. So what is the benefit or some of the limitations of this min cut? Benefit, we can say that this framework is incredibly powerful. It is efficient and for a wide range of problems. It provides a globally optimal solution. This means we do not have to worry about getting stuck in a local minimum. We know we have found the best possible segmentations according to our energy functions, right? So these are some of the benefits over that. Then what about the limitations of this min cut? The basic model is designed for a simple binary segmentations. What is the binary segmentations here? As we discussed before, the foreground and the background is considered as a binary segmentations. So these are the two components available in an image. We have to segment it. We have to separate it from the foreground and to the background. So, however, it can be extended to handle the multi-level problems. But although the computational cost is increased, we can do it, but at increase in the cost. So we can't say this is a more effective one. So this will be considered as some of the limitations over that. So the last topic of the slide is that real world applications. So we are discussing about the power and the efficiency of a graph cut. I made them to go to a tool for many vision tasks, right? So the first one is the interactive segmentations. The perfect real-time example is interactive image segmentations, such as GrabCut tools. The user draw a rough box around an object that want to segment it basically. The computer then uses this rough outline, that's what we call as the edges, to set up a graph's edge weight. That is what the pixels inside the box have a strong connections to the source, that is S, and the pixel outside have strong connection to the sink, that is what is called as a T. So the algorithm then quickly find the min cut to create the pixels or the precise professional looking segmentations. So this is one of the most important real world applications for this min cut. Then what about the other applications here is that beyond segmentation, the energy minimization framework is widely used for image restorations. We have seen the unit 1 itself. So what is that? It is removing a noise or a blur from the image by defining an energy function that penalizes solutions that are inconsistent with the original images and are not smooth, right? And what about the next application is the stereo matching. We are using a fingerprint. So finding a corresponding point in two images taken from a different viewpoints to create a 3D depth map. This we are using the real-time applications of Egypt to find the mummified face in a pyramid. So the energy functions can be defined to favor the matches that are both visually similar and have consistent depth. Applications of feature detections and segmentations. So we have spent time learning the core techniques of the computer visions, right? So how to find the points, edges and segmentations we have seen a lot. Now let's explore why these skills are so vital. These methods are not just academic exercises, or they are the foundation for some of the more exciting technologies in the world. Let's see some of the applications in the real world. First one is the atomic vehicles or the autonomous vehicles. Let's start with the most talked about application is that a self-driving cars, eyes, are its cameras and sensors, right? So it uses a feature detections to identify the key landmarks like road sign and the lane signs. So these are the basic thing or the input for that car. But for some complex understanding, it relies on the segmentations to classify the every pixel in its view. It has to differentiate between the road and the opposite car or the vehicles, as well as the traffic lights rules corresponded to that. So separating the road from the sidewalk and identify the pedestrians and other cars, it's how the car sees. It's surrounded in the real times. So basically, it have to visualize the features and segmented it, and according to that it have to act it. So what about the medical images where we are using? In medicine, segmentation is a lifesaver, as I say. It allows the computers to precisely outline the organs, examples x-rays, the tumors or other anomalically structures in a MRI scan or a CT scans. Example, brain tumor, many things so on. So this helps doctors with diagnosis, allows them to measure the tumor size and plan surgical procedure with incredible accuracy. So this is a crucial high-stake applications where precision is everything. Even starting from the operations to detections, everything, we have to more accurate and precise over that. Then third is the robotics. So robots need to see to interact with the world, right? We talk about AI, types of AI where actuators act and defend over that. So these use the features detections for navigations and to identify the objects to grasp. For example, a robot in a factory can use a fast corner directions to quickly find a specific part on the conveyor belt and pick it up fast. So this is a key part of the stimulation, localization and the mapping. We call it a SLAM. Stimulation, localizations and the mapping, where a robot builds a map of its environment as it moves through it. So these are some of the foundational applications. But there are still many more applications in a creative and a practical applications too. So beyond the big and obvious examples, these techniques have found their way into many everyday and specialized applications. Let's talk about the augmented reality AR, VR. Have you ever used an AR app that places a virtual object in your rooms? Or we can say some of the games over that to visualize the Jurassic Park or maybe the past years over that. So, and it stays perfectly in place. That's because it uses SIFT algorithms and the self feature algorithm to recognize the real world objects. And the anchor and the features or the virtual content of them was distributed using these two algorithms. The app finds unique points on a surface like a tabletop and uses them to keep the virtual objects stable no matter how you move your phone or grab it. So the image editing is that the interactive tools like for example, GrabCut in a photo editing software shows how powerful the GrabCuts can be. A user draws a rough outlines around the person, and the algorithm uses an energy-based models to find the most accurate segmentations effortlessly, removing the background. So next we can say about the video surveillance. So in security, these techniques are used to automatically track subjects. We have some night vision cameras or morning vision camera where we can capture the 360 degrees also. So that segmentation and trackings are combined to identify a person of interest and follow their movements in a crowded areas which can be greatly assistant in a security analysis. For example, in bank, if there is any movement or the motion captured, it will directly take the picture of that images or the surroundings in all 360 degrees. So the content-based image retrieval is that when you search for an image, the results are often based on more than just keywords. So the system uses features descriptors to find images that are visually similar to your query images, which is invaluable for a wide range of fields from police database to hard history. The next one we can say about the specialized and emerging applications. Finally, let's look at some other important applications that highlight the versatility of these methods. So first one is a quality control. In manufacturing, every product needs to be perfect. The computer vision systems on a production line use segmentation to inspect product from the defects like line cracking, or tiny cracks, patches, or the scratches or misplacement spots. This automated process is much faster and more accurate than the human inspectors. Then what about the satellite image analysis? So analyzing the satellite photos is a huge task, right? But segmentation makes it manageable, a part by part, instead of taking all of one. If you are segmented and do the work, it is a more manageable task when compared to the other. It helps to classify land use, identify the architecture field, track deforestations or the desert area or the river area. Like that, it will be segmented and separated or monitor the changes in the urban areas over the times. Then what about the facial recognitions? At its core, the face recognition relies on the feature detections. It can be OpenCV or any PyCharm, anything. Feature detection is a main task of the face recognitions. So algorithms finds key features on a face, like the corner of the eyes and the tip of the nose, and use them to align the face and then recognize it. This is a classic example of these methods in actions. Facial recognition is used in a wide range for security purpose or authentications, and so on. So this is a classic example, as I tell, because it's used in everything from phone security to the law enforcement. As you can see, the ability to detect the features and the segmentations and image is not just a technical skill. It is a foundation of a huge range of applications that are shaping our world, right? So this is more than just an applications. There are so on in this. You have to study more and more on this. But there are still some limitations over that. Let's see about that. The limitations of traditional methods is that first we'll see about the environment and contextual limitations. So we have spent a lot of time discussing what the traditional computer vision methods can do. So now it's time to be honest about the shortcomings, right? So the limitations, these classic approaches are precisely what fueled the next major revolution in the field. Let's start with their biggest weakness related to this real world. So the first one is that it's sensitive to the environment. Yes, it is. One of the most significant problem is that these methods are fragile, so weak, and a change in lighting can completely throw them off. A simple shadow can create a fake edges, and a low light environment can make a real edge. So it is a misunderstanding tricks disappear entirely. So this is because these algorithms relies mostly on the simple precise pixels intensity changes, and shadows and pool lighting directly manipulate these values. So once the input is wrong, everything will be flop. So the lack of semantic understanding is that this is a fundamental issue basically. A traditional algorithms can find a line or a region of a similar color, but it has no idea what that line or the region is. It cannot tell you that the segmentation blob of the pixel is a car or the corner belongs to the book. It lacks the ability to understand the meaning or the context of the objects it is processing. So it's like being able to read the letters on the page but not knowing what the word means. So it can read but cannot understand. So ignoring the context also is another major limitations. These methods often analyze pixels and features and isolations basically. So they don't take the bigger pictures into an account. For example, a traditional methods would know that the person is likely standing on a road and not flaunting into the sky. The lack of the global contextual view makes them prone to error in a complex real world scenes. So this is another issues when we talk about the limitations. The next one is regarding the noise and the clutter. So the world is a messy place. Everything is here, starting from a normal insects to the normal things available in the real world. It's so messy. So noise in an image can create countless fake edges in an image and the features. So while background clutter can confuse the segmentation algorithm, so the algorithms are trying to find patterns, but the noise and the clutter creates so many distractions that the true pattern can get lost. So now let's talk about some of the practicals or the computational limitations for this. So in addition to their environment weakness, traditional methods have some significant practicals and computational drawbacks, right? So first start with the manual parameter turning. This is a huge pain point for engineers. Many of these algorithms require manual tuning of parameters. For example, with the Canny Edge detector, you have to manually set the high and the low threshold. With mean shift, you have to choose a bandwidth. Getting these parameters right is often tedious process for trial and error, and setting that work for one image may fail completely on the next. What are the computational costs for this is that some of the most accurate method like normalized cut as we discussed before are simply too slow for real-time applications. They require solving complex mathematical problems and processing a single high resolution images can take several seconds or even a minutes. So this makes them unsuitable for things like autonomous driving or video surveillance where decisions need to be made in milliseconds because of this delay thing. The next one is a scale and the viewpoint variance. So the while algorithms like SIFT or SURF were designed to handle this, many simpler methods are not robust to change in an objective size or the viewpoints. Features are easily detected from one angle might be unrecognized from the another. This makes them brittle in dynamic environment basically. So in efficient features descriptors, even the powerful SIFT and SURF algorithms have limitations. So these descriptors of the fingerprint, as I mentioned before, can be quite large. This makes them computationally expensive to match and can be a problem for devices with limited memories also, like a small robot or a mobile phone we are using, so on. So these are some of the limitations. Added to that, over and under segmentations is also one of the problem here. When it comes to segmentations, the classic methods often struggles to find the right level of detail. A method like split and merge might either produce too many tiny meaningless segments that we call as over segmentations, or to fail to separate incentive objectives basically. So that could be a different like under segmentations. The next one is the binary nature of a graph cut. Finally, while graph cuts are incredibly powerful for energy minimization, the basic model is designed for binary segmentations. Separations of foreground objects From the background, as I told about the two components in an image, foreground object as well as a background. So the extent in these framework to handle the multiple labels. Example, a segment in a car, a person, and a tree all at once from an image. It's a complex and a computational challenges over and over again. So far we have discussed about some of the limitations and challenges over this, but there is some changes and evaluation in this field. So as well as the future things for this technologies also, we'll discuss on that. So the changes and evaluation of the field is that we have talked about the limitations of the traditional computer visions. Now let's explore the revolutionary changes that have addressed these problems and transformed the field. The biggest shift has been the move from the handcrafted features to the learned features. So the shift from the handcrafted to learned features is that in the past we have manually designed algorithms like SIFT or Canny to find the specific features. Today we are trained with the CNN models, convolutional neural networks, on a massive data sets, and they have learned what useful features is on their own. The networks automatically discovers a hierarchy of features from a simple edge in the first layer to complex objects in the deeper layer. So end-to-end solutions. This shift to learn features has enabled end-to-end solutions. A single neural network can now take a raw image as input and directly produce a desired output like segmentation mapping without any intermediate steps. This simplifies the entire pipeline and reduces the need for the multiple or manually tuned algorithms. Improved robustness is that because CNNs learn features from a huge variety of data, they are far more robust to variations in lighting, textures, and oscillations than the traditional methods. A learned model is less likely to be fooled by shadows or noisy images. So what are the real-time performance here? These modern models, when optimized and run on the GPU, can perform tasks like segmentations and object detections is a real time. This has opened the door for the critical applications in robotics and autonomous driving that were previously impossible due to the computational cost. The semantic and instant segmentation is that the deep learning has allowed us to tackle more complex segmentation tasks. Semantic segmentations classify every pixel into a category, example road or a tree. But even more advanced is the instant segmentations, which can identify and label each individual objects in an image, differentiating the car 1 from car 2. Some of the new architectures here is that the field is rapidly inverted from the new networks architectures specifically for the vision task, the unit architectures. For example, is famous for its use in medical image segmentations, while the Mascar CNN is a state-of-the-art models for instant segmentations. So these are some of the changes for the future trends. There are also some future directions on the ecosystems. Beyond the algorithm themselves, the entire ecosystems around the computer visions has evolved, and we are now looking at some exciting new frontiers. So open source frameworks like the widespread availability of a powerful open source libraries like TensorFlow, PyTorch, or OpenCV for facial recognition as democratizes the field. So these frameworks provide pre-trained models and tools that allows the developer to build advanced vision system without having to start from the scratch. So this are all added advantages. What about the hybrid model? While deep learning is dominant, some systems uses hybrid models that combines the best of both worlds. For example, a deep learning model might perform the initial segmentations, and then the traditional graph cut algorithm is used to refine the final boundaries for a perfect clean result. So from 2D to 3D, we are moving beyond flat images, right? So the future is focused on the 3D scenes understanding to understand more precise accurately. So using the data from the sensors like LiDAR and the depth camera, this provides a more comprehensive views of the world, including the depth and the volume of the objects, not just their pixels values. So there is some rise of the explainable AI because the XAI as deep learning models become more complex. There is a growing push for XAI for critical applications like medical diagnosis or autonomous driving. We need to understand why a model is made of a particular decision. XAI aims to specifically provide insight into what features a model is learning and why it arrives at a specific conclusions. So in summary, the field has transitioned from the relying on human intuitions to leveraging the power of data. So this shift has now not only improved the performance and the robustness, but also open up a whole new world of applications that were once confined to science fictions. So the future will not be about creating even more intuition, reliable and intelligent vision systems. Now let's go into the topics of future of feature directions and segmentations. So we have discussed about the 2D and 3D images. So beyond 2D images, we have spent a lot of time in this. But this field is moving at an incredible pace. The future is not just about analyzing flat 2D images. It's about building systems that are truly understand the world is a richer, more human-like way. This session will explore the most exciting frontiers. So the 3D scenes understanding. The next frontier in moving beyond pixel to 3D scenes understanding, as we discussed before. The future system will not just look at a single image, but will process the data from the multiple sources like LiDAR, or RGBD cameras which captures the colors and the depth, and multi-camera systems. This allows for a real-time 3D segmentations, giving us a more comprehensive understanding of a scene's geometry, volumes, and relationship between the objects. This is critical for applications like autonomous navigations and robotics, where knowing the object's distance and the size is critical. The multimodal fusion is to achieve these robust. Understanding future system will rely on the multimodal fusion. So this means combining the information from different types of the sensors. Think of it like a human using their eyes and ears to understand their surroundings, just like a sensors. A self-driving cars of the future will fuse data from the cameras for color and texture, LiDAR for the precise distance, and the radar for motions and bad weather directions to create a single and unified and more reliable pictures on the environmental. So the dynamic and the temporal segmentation is that the world is not just static, it's constantly moving, or its traditional methods often treat each images from an isolations. So the future visions is dynamic and temporal segmentations. This means models will not just segment objects in a single frame, but will understand how they move and change over time in a video. This is essential for tackling objects, analyzing human actions, and making predictions about future events in a scene. Then, what about the futures of AI and data? Beyond how we precise the world, the future of computer vision is also being shaped by advancement in AI and how we handle data. So the generative model is that a huge problem in a computer vision is the need for the massive hand-labeled data set, which are expensive and time-consuming to create. So the generative models like GAN and diffusion model will help to solve this. So these models create highly realistic synthetic data that can be used to train the other models, providing the virtually endless supply of labels, images, and reducing our reliance over the manual annotations. As we talk about the self-supervised learning, to address the data problem from the another angle, self-supervised learning is becoming a major paradigm. These models are trained on a vast amount the unlabeled data by solving a pretext task, like predicting a missing part of an image or the pixel's color from the neighbor for using for the training purpose. So this allows a model to learn the powerful general purpose features without any human labeling, which can then be used for segmenting the other task. Some of the real-time segmented scenes graph is that the ultimate goal of the scene understanding is to go beyond the simple labels. Future models will create real-time segmented scenes graphics. This means the system will not just segment a person or a bicycle in the background or the front end, but will understand the relationship between them. A person is riding a bicycle in a futuristic tense. So, this level of understanding is vital for complex robotics tasks and intelligence agents. It's already in on work in a research. Then about the HEI and TinyML is that as models get more efficient, they are moving from the cloud to the device. The AGI and the TinyML machine learning are about running powerful AI algorithm directly on a low power embedded systems like smartphones or drones. This enables a real-time processing without a cloud connections, which is crucial for applications where the latency is a concern, the privacy is a priority. So we talk about the XAI, explainable AI, for safety critical applications like autonomous driving. We cannot have a black box and that just makes a decision. We need to know why. The future of vision will involve explainable AI, where models can provide insight into the decision making process. This builds public trust and helps the engineer to identify and correct the errors. So let's go for some of the summary of this unit from handcrafted rules to the learned vision. So in this unit, we have explored the core building block of the traditional computer visions, moving from the most basic element to a sophisticated framework for an image understanding. We begin with the points and patches. Points and patches, the first topic, and the fundamental local features that act as the image, just fingerprints, right? So we then build on this with the edge and lines, which represent the objects and the boundaries and the geometrical structure, offering a more abstract representations of the scenes. So from there we have developed into a segmentations, the critical task of partitioning an image into a meaningful region. We examined varieties of approaches from simple split and merge techniques to a more advanced statistical methods like mean and shift. So which finds a cluster to pixel based upon the color and the spatial proximity. So the unit cumulative or culminated in the powerful and elegant framework of the graph cuts and edge based methods. This approach redefined the segmentations problem as one of the energy minimization, providing a robust and a globally optimal solution for the wide range of the problem. We saw how this framework's rooted in graph theory, right? So transformed the problem of image segmentation into a solvable puzzle is a big orientation sphere. So ultimately, this unit has demonstrated the progressions of computer visions from the field of handcrafted tools to one of the powerful automated frameworks, OPSO. So the method we have studied from the edge reduction to the graph cut forms the foundation of many modern applications. So, however, we have also highlighted the limitations and the sensitivity to noise, lack of semantic understanding, and computational cost. So I hope these limitations are precisely what set up the stage for the next great revolution in the computer vision field, deep learning, a topic that builds upon these foundational principles or the principles to create the models that can see and understand the world in a way we are only beginning to fully grasp. Thank you.